Good day, Dr. Faiz. Today I will be presenting about the introduction to our project, which is the design of half adder using NMOS PTL Pass Transistor Logic. So what is IC design? IC design is the process of interconnecting circuit elements to perform a specific desired function, while a half adder is a combination logic circuit that is designed to carry out addition of two binary digits. So from the figure above, we can see of the block diagram, also the circuit diagram of a half adder. So from the circuit diagram, we can notice that an S or OR gate and also an AND gate are used to implement a half adder. So for the NMOS PTL, it acts as a switch that will transfer the input signal to the output with a control signal that will determine the transistor state. Moving on to the working principle of our design, we can know that NMOS PTL will only pass strong logic 0 and degraded logic 1. So for the sum function of half adder, it is implemented using an S or OR gate. So for example, when A is equal to 0, the output S will be dependent on B, while when A is equal to 1, the output S will be inverted B. So for the carry function carry output, it is implemented using an AND gate. So when both inputs are 1, the degraded logic 1 will be passed, while in other cases, the output will be 0, where it is shown that the output are all full low.
My name is Daniel Jais. Now I will explain methodology part. Okay, for review, each project we design a half adder circuit using NMOS Pass Transistor Logic or PTL. The design was fully developed using the Cadence Virtuoso software suite. Our focus was on creating the schematic, running simulation, and building the layout, all while targeting at a 19nm CMOS technology using the GPDK090 library. The analog IC design flow is illustrated in the figure. The analog IC design flow and Cadence tools involved. And then for setup in Cadence Virtuoso, we began by setting up a new design library in Cadence in software and linking it to the GPDK090 technology file. The schematic for the half adder was then constructed using only NMOS transistor to form XOR and AND logic gates without incorporating any CMOS inverter. The three figures below they illustrate the initial virtual setup, library creation, and instance selection from the GPDK090 library. Schematic design and verification. Once the schematic was completed, we conduct an electrical rule check to ensure all the connections are valid. A symbol of the half adder was generated for hierarchical design. We then create a testbench that includes a logic voltage source and a capacitor load for accurate simulation. And then simulation analysis. We carry out three types of simulation: a transient, a DC, and a DC. This simulation allows to us to verify the functional of our half adder and design under a different electrical condition, where output were analyzed to confirm a correction logical behavior. A display a simple waveform will provide a better insight. And then layout design. We move on the layout phase using the virtual layout editor, and mouse transistor were placed and routed with a carefully planning for multi-layer routing of input, output, and power. A design rule check was then performed to ensure compliance with the physical design rules. The figure may include the layout view and the DRC result. Layout validation. After the layout was complete, we perform a layout versus schematic check to ensure consistency between the layout and the schematic. Post-layout simulation, we are also carry out incorporating parasitic element to observe a realistic performance result. Any visual results such as LVS regression or post-layout waveform may be presented. Documentation content. Throughout the design process, we thoroughly documented each stage, a screenshot were taken the DRC and LVS result were saved, and a simulation waveform were captured. This ensure full traceability and validation of the half-adder design using NMOS PTL logic. A visual summary can help demonstrate our comprehensive demarcation.
After complete building this circuit, we try to save to check if there's any error. So there's no message popping up. So another method we can check the error messages from the Virtuoso. So at the end we can see there's the circuit has been saved, so no error message. So now we can check the symbol. So this is the symbol from the schematic of the component, and the mask also has its own symbol built inside of it. Then so from this I will check the DRC. Before that I need to open up the layout. So the layout is opened from the layout Excel, and we click OK. So this is the layout from the one of the components, which is the NOT gate. So to check this, we go to the Sura and run DRC. So make sure this is correct and this is checked to GPT. Okay, yes. So wait for a while. Check the DRC. We have to wait until it's completed. So as we can see, do you want to? Yes. No DRC. Alright. So next we will check the LVS for cross-checking between the layout and the circuit. So make sure that both are same. We are checking from the schematic and layout, and as usual GPD, click OK. OK. So wait for a while. Okay, so it matched. Yes. So we can see the circuit is connected, and then layout match. Layout and schematic is matched. So as for now, we will check the result, waveform, and the power efficiency. So this we set for 100, and from the schematic we put the what we call the measurement, 2 inputs and 2 outputs from the sum and carry, and click OK. So we just run. Separate. Okay, we got this waveform as per the research paper. So now we will check the power efficiency. will set this 50. You can set until 100 or 50, either one. Now we save, we check all, click OK. Now from the user browser, so the result for the power efficient is already loaded. So as we can see, we go to this power, double click, okay, we separate. So as we can see, we can get the power efficiency result.
Hi, my name is Nurul Atira. Today I would like to briefly share with you the advantages and disadvantages of our half-adder design using NMOS Pass Transistor Logic, which we implement to Cadence Virtuoso. So the first advantages is the design of NMOS Pass Transistor is very efficient in terms of transistor count. By using the NMOS Pass Transistor, we were able to reduce the number of transistors significantly compared to the conventional CMOS design. This directly leads to a small layout area, which highly beneficial in integrated circuit where the space is very critical. And secondly, with a few transistors and reduced switching activity, our circuit demonstrate lower power consumption. So in our simulation, the average power consumption was clearly the lowest compared to our research paper. This makes NMOS Pass Transistor Logic is a great choice for lower power application such a portable and battery operation device. However, despite the advantages, there are also important limitations that we know and we acknowledge. One of the major disadvantages is the voltage degradation. When the NMOS is used to pass a logic 1, the output level is not the fully supplied voltage, but it reduced by the threshold voltage. This incomplete voltage swing can lead to unreliable logic detection in the next stage on circuit. Thank you.
In the conclusion, the half-adder design using NMOS Pass Transistor Logic and Cadence Virtuoso achieve reduced transistor count, lower power consumption, and compact layout. Despite voltage degradation issues due to NMOS threshold drops, the design passed all functional and layout checks, proving PTL as an efficient approach for low-power, area-efficient digital circuit design. That's all from us. Thank you.